Hello everybody, my name is Vladimír Šulc, and in my presentation I will tell you where is the IQRF going to. Just a short introduction. I'm active in the field of electronic over 30 years. My IQRF company was founded already during my university studies in 1991. From the same beginning I focused on wireless communication. Last almost 20 years I specialized in mesh networking algorithms. I'm participating in IARIA conferences since 2009, and thanks to Ph.D, I became IARIA Fellow around 10 years ago. On this slide, you can see just a few projects I have participated in. Since 2006, Micros closely cooperates with academics, mainly with Brno Technical University and with Technical University of Ostrava. Our cooperation and mentioned projects are nice examples of cooperation between industry and academics. All mentioned projects have been co-financed by Ministry of Industry and Trade, Czech Republic, and I'm also proud for nice results of these projects. So, big thanks to our academics partners helping us to see topics also from different perspectives, and to our Ministry of Industry and Trade for helping us to move our R&D forward. Here you can find program of my presentation. Mr. Smarty will help me to take you through the topics. In the same beginning, I will briefly introduce what's the IQRF and how can we classify it. And of course, because I'm the IQRF evangelist, I will mention also reasons why to adopt the technology. In the next part, which will be more technical, I will focus mainly on detailed explanation of protocols behind the IQRF and also on mechanisms assuring industrial reliability and real low power. From protocol descriptions, I will jump to the next important topics for IoT. Interoperability and security. Okay, let's go directly to the first part. What's the IQRF? The IQRF is a wireless mesh technology firstly introduced to the market in 2004. Since then, it provided wireless connectivity to more than 500,000 devices worldwide. When I'm talking about IoT, I am always saying it's a big playground with many players and many technologies. The IQRF provided just few pieces to this big puzzle. Let's take a look. What is the IQRF today? There are protocols, implemented standards, security elements, components, tools, both software and hardware, devices, applications, clouds, services, systems. There is also IQRF Alliance promoting the IQRF technology. Thus, I can proudly say that IQRF is not just a technology anymore. Since 2004, it evolved into a fast-growing ecosystem and a horizontal platform for building a variety of vertical solutions. When I'm talking about positioning, I should say in the same beginning, the market is deeply fragmented and there is no globally accepted standard. Consequently, there are many different wireless technologies available in the market, and some of them we are using on a daily basis. For example, ANT, Wi-Fi, Bluetooth, or mobile communication standards. There can be a lot of different ways for sorting them. In this positioning, I group technologies according to communication range, because communication range often predetermines the purpose of use. According to communication range, we are often classifying wireless networks as wireless personal area networks, wireless local area networks, wireless neighborhood area networks, and wireless wide area networks, with short, medium, and long range. thanks to the point-to-point communication range around 500 meters, and thanks to reliable mesh networking capabilities supporting up to 240 hops, the IQRF perfectly fits many applications from short to medium range. On the previous slide, I mentioned the market of wireless technologies is deeply fragmented due to many limitations. These limitations can be technical, legal, or application concerns. When we are talking of technical limitations, we can mention, for example, lack of bidirectional communication, no routing, communication range, communication speed, or limited power budget. No or not efficient bidirectional communication can lead to maintenance and security issues. From the same reason, such technologies cannot be used for control or automation. No routing capabilities often leads to problems with obstacles or to cover difficult areas like deep indoor. Lower communication speeds are often used to increase communication range. On the other hand, they bring higher latencies and also higher power consumption. Higher communication speeds, on the other hand, results in higher consumption, and such technologies often cannot be used for battery-operated devices and applications. In this short introduction part of my presentation, I will focus also on reasons why to adopt the IQRF technology. On previous slide, I mentioned market fragmentation due to the technical or legal limitations. The IQRF is tuned to IoT applications and able to overcome many of mentioned limitations for its application scope, control systems, lighting, and monitoring. Most of mentioned limitations are related to the lack of routing capabilities. I am happy to say the world rediscovered beauty and urgency of the wireless mesh networks because the IQRF is a true wireless mesh technology. As you will see in the technical part of my presentation, the IQRF uses protocols, dramatically increasing robustness and reliability. This is, from my point of view, the basic differentiation of the IQRF. Applications and community of users will benefit also from technical uniqueness, great technical specification of the IQRF transceivers, such as from other IQRF attributes, simple integration, interoperability, low power, and security. The IQRF is open and growing ecosystem, enabling straightforward applications development. Let's take a look to the IQRF on the timeline. From it, you may see where the IQRF is going to. Of course, it's up and to the right. The IQRF mission is to deliver low power, simple to adopt, secure, interoperable, and open wireless mesh connectivity for IoT. In this slide, I put on the timeline also protocols to show how the IQRF was continuously developed over the time. And in the next part of my presentation, I will focus on technical description and visualization of these protocols. The first technical topic is description of IQmesh and FRC protocols and their impact to reliability. When we are talking about routing in wireless mesh networks, we should mention it's a big technical challenge. Why is that? I often demonstrate routing in wireless mesh network on navigation in our car. In wireless mesh networks, we deliver messages from point A to point B through the nodes connected by wireless links. The analogy in navigation is the same. We are going by car from city A to city B. We are going through different towns which are connected by roads. Some of towns have direct connection between each other, while to some towns we should go through other towns, depending on the road's network. With longer distances, it's more and more difficult to find optimal way. Thus, for traveling comfort, most of us are using mapping and navigation software, finding for us ideal way to go. During routing in wireless mesh networks, we should solve exactly the same problem. With increasing number of communication devices, there is exponentially increasing number of possible links between devices. In our mapping analogy, we are talking about roads. On the right side, you may see dependency between maximal number of links in such topology and number of nodes. The basic difference from map and navigation is that software we often run on our smartphones. The same technical problem, because of the price, we should solve on a small microcontrollers with hardware resources mostly million times lower than we have on our smartphones. Besides that, we should solve this in real time to avoid latencies. This brings big technical challenge, and routing in wireless mesh networks was often topic on many R&D papers presented on scientific conferences. Let's take a look at some algorithmic approaches. Probably the most often used approach is ad hoc routing with some kind of routing vector. Our task is to deliver messages from coordinator to node N3. In ideal world, it's perfectly working. We are going through nodes N1 and N4. And that's it. Just 3 hops. In our real world, the situation will be different. Due to the interferences or obstacles, which often vary in time, we cannot expect every link as reliable, but we can illustrate it as blocked by the wall. In this case, the same strategy will fail. Let's take a look to the animation. As the first, coordinator delivers message to node N1. N1 resends the message, but it's blocked by the wall. In this case, message should be written back to coordinator to try another path. Finally, the message is delivered to the final destination through nodes N5 and N2. On this simple example, we can see particular confirmations are needed to assure reaction to the broken link. In our case, such optimized routing results to 11 hops. Now we will take the same topology and I will show you how it will work with IQMesh routing protocol. Coordinator run, usually during installation, process called discovery. During discovery, the network is rearranged for routing and each routing node receives special number we are calling virtual routing number. This number is unique and reflects distance of each node from coordinator. This virtual routing number will be further used for routing. Original node identification, it may be address, MAC, MID or anything else, will be used only for addressing. But virtual routing number will be used for routing. Consequently, TDMA and oriented flooding is used during routing. Oriented flooding means that each routing device has dedicated time slot according its virtual routing number. When nodes receive message, they will make simple calculation between its and sender virtual routing number and waits number of time slots between repeating or routing the message. It will look like that. Coordinator initiates communication and delivers message to nodes N1 and N5 with virtual routing numbers 1 and 2. Consequently, in the next time slot dedicated for node with virtual routing number 1, node N1 resends the message and this transmission fails because of the broken link. But it's not a problem, as node with virtual routing number 2, which slot is consequently coming, already received the message in the 0th time slot. So it will simply resend the message. In this case, it will be delivered to the nodes N4 and N2. Then, node with virtual routing number 3 has its active time slot. So the node N4 resends the message, and after that, in the next time slot, also node N2. And finally, we are done. We needed just 4 hops, therefore only 4 dedicated time slots. You can even see redundancy in the network. And this redundancy dramatically increases robustness and reliability. IQMesh algorithm is very simple to implement and require only few hardware resources of the microcontroller. The routing process is collision-free and fully deterministic. Thanks to the oriented flooding, there is no need for partial acknowledgements, and it's proven in variety of real applications. The IQRF, thanks to the IQMesh protocol, defined totally new level of industrial reliability for wireless mesh networks. It's basically assured directly by the routing IQMesh protocol principles. Contrary to some wannabe optimized routing protocols, focusing only on time optimization, IQMesh routing protocol is focused on robustness and reliability. And this is exactly basic need of every industrial application. Now, I will describe and visualize another tricky protocol behind the IQRF. It's named FRC, Fast Response Commands. Primary purpose to define this protocol was data aggregation. This is another big challenge in wireless mesh networks. The reason for it is very simple. You have already seen routing as an algorithmic challenge. Now, try imagine typical situation. You have to collect data from all sensors in the same network. In the star network topology, typical way how to realize aggregation is polling. It makes sense to use it, and there is a lot of different implementations from step-by-step request confirmation for each node to one request from coordinating device and TDMA organized answers. But, contrary to the star network topologies, we have totally different situation in wireless mesh networks. Polling requests should be also routed the answers as well. With this approach, time responses for data aggregation exponentially grows with the number of nodes connected to the network. Thus, to decrease time latencies for data aggregation, we have designed and verified FRC protocol. This protocol can be perfectly used also for collecting answers from devices for broadcasted commands. This is very important, especially for industrial systems. Try imagine we have lighting system and we should switch on each single light. It's a good practice in industry to get confirmation that our request was successfully delivered and processed. And FRC is perfect solution for this need. How it works? Try imagine you will first broadcast your request. This will be realized by the IQMesh protocol already introduced. It's based on oriented flooding, thus very reliable. The final aggregation will be realized by step-down collecting data, deploying effectively rearranged mesh network with virtual routing numbers. You can imagine that as a train collecting wagons from the most far to the closest node. Let's take a look to the following visualization. FRC protocol consists from 3 phases. In the first phase, coordinator broadcasts FRC requests with information what should be processed or collected. In the upper right corner, you can see the timer displaying elapsed time for this phase. Broadcasting is realized by the IQMesh protocol and utilizing TDMA and oriented flooding. During that, each routing node have dedicated time slot based on its virtual routing number. This assures reliable and fast delivery of FRC requests to all network nodes. Now, please focus on red numbers at each node. These are virtual routing numbers dedicated to each node by the coordinator during the discovery process. On the bottom, we can see frame with time slots. During visualization, you will see which node is active. Okay, let's see the broadcast process in real. First, coordinator sends the FRC request. It's standard radio communication, so transmitted request is received by each node in the communication range. In this case by nodes N1 and N5. Now it will progress in the same way from node with virtual routing number 1, then 2, 3, 4, and 5. On the timer, you can see it took 300 milliseconds. We can see also that each node received FRC requests few times. As already mentioned, IQMesh routing scheme dramatically increases robustness and reliability. Even if some local links are broken, the broadcasted requests can be automatically delivered via different paths. In this moment, each node has available its own data only. Therefore, you can see wagons at each node loaded by their own data. During the second phase of FRC, each node will transmit its own data. This starts from the node with the highest address in our case from node N5. Then it will progress through nodes N4, N3, N2, and finally N1. Now we can see each node have already collected data from other nodes in its neighborhood. In our case, for example, node N4 have already collected data from all other nodes. Now, let's merge collected data to wagons. We have loaded or received data to wagons, and they are ready for the last phase, for aggregation. The aggregation process we can imagine as the train collecting wagons with data. It's processed step by step, starting at node with the highest virtual routing number, and finally delivering wagons to the coordinator. In this phase, each time slot is 60 milliseconds long. So let's start aggregation. Train will deliver wagons from nodes with virtual routing number 5 to nodes N2 and N4. Now, the train is ready at the node N4 because it has the second highest virtual routing number and will deliver two loaded wagons to all nodes with the lower virtual routing number in its neighborhood. In this case, to node N2, N5, and N1. The train is now ready at nodes N2 with virtual routing number 3, and it will deliver 4 loaded wagons to node N5 with virtual routing number 2. As I already mentioned, the train is going always from nodes with the higher virtual routing number to nodes in their neighborhoods with the lower virtual routing number. Now, the train proceeds in the same way and delivers loaded wagons from node N5 with virtual routing number 2. For algorithmic simplicity, coordinator has dedicated virtual routing number 0. Finally, the train will take wagons with data from node N1, which has the lowest node's virtual routing number in our network. And we are done. You can see high level of redundancy. It has dramatically positive impact to the reliability and robustness. In the previous visualization, I demonstrated how FRC protocol solves big algorithmic challenge to efficiently collect data in wireless mesh networks. Simultaneously, it assures industrial reliability and robustness, which is a must for any control or automation system. Regarding timing details, you can use the red link to the IQMesh timing calculator. Next topic of my presentation is related to the consumption aspects and protocols enabling design of truly low power devices. Why true low power? I believe almost everybody of you already met eye-catching wording like extra, super, or ultra low power. These abstract words say nothing about real consumption. For example, many years ago we had a booth at Electronica exhibition in Munich. In neighboring booths, the company presented 3 milliamps consumption in RX mode as an ultra-low consumption, and it was the main motto on the booth. When visitors came to our booth and asked me if we have also ultra-low consumption for our modules in RX mode, I should answer that I don't know if it is ultra-low enough, but our 200 micrograms in LP-RX mode and 20 micrograms in XLP-RX mode are much lower than advertised 3 milliamps on the neighboring booth. The same situation comes with often used wording like 10 years on a battery with asterisk sign, saying something about limitations of the application. For example, when the data, for example temperature, is sent only once a day. It means useless application if temperature is monitored just once a day, and in reality, such device sends just few thousand messages during the whole life cycle. I should say that even our engineers created pills like 1000 years on a battery in deep sleep modes. These are just few reasons why we registered trademark IQRF True Low Power and why we are talking by the application language instead of advertisement language. In our case, we are not saying send data once a day to prolong battery life, but we are saying send them as often the application should do, and then easily calculate life expectancy from the number of packets. In our case, we are talking not about thousands or tens of thousands transmitted packets. We are talking about millions of transmitted packets. The IQRF transceiver modules achieved really low consumption thanks to the excellent PHY specification and also thanks to the protocols I will introduce in the next few slides. Beaming protocol was introduced in 2021. It's simply natural. Each battery-operated sensor sends all its data in one packet periodically, as it is convenient from the application point of view. These non-routing sensor devices have the yellow color. Data are collected by all repeaters in sensor's neighborhood, as you may see from this animation. Repeaters are blue nodes with red virtual routing numbers. Together with the beaming, also offline FRC protocol was introduced. It's innovative FRC protocol I showed you in previous slides. This protocol is used for collecting data from the beaming. As you can see, the basic difference is that data are already available on repeaters. Therefore, there is no need to send them locally, like we did in standard FRC protocol. Offline FRC protocol has only two phases: broadcasting of FRC requests and aggregation. Let's visualize them. As the first, I will show you broadcasting FRC request. It's initiated by the coordinator. It's consequently spread over the network from node with virtual routing number 1 to the node with the highest virtual routing number. In our case, number 2. Now, the process will go on with the aggregation phase. And again, it works in the same way like with standard FRC. Data aggregation, in this case visualized as wagon loaded with the data, starts from the node with the highest virtual routing number, and it's propagated step by step to the coordinator. In our case, just through nodes. I have visualized the process of beaming and consequent data aggregation. This mechanism brings great specifications to real sensors. On the picture, you can see industrial temperature and relative humidity sensor. It works on one lithium thionyl chloride battery of standard AA size, and it's transmitting its data every 1 minute. Life expectancy for this mode is 10 plus years, and it's limited mostly by the self-life of the battery. Theoretical life calculated from the real consumption is 21 years, and during this time the sensor is capable to send over 10 million packets. On the picture below, you can see detailed state diagram of the sensor. From this state diagram, you may see the sensor is not just blindly transmitting its data, but before transmission, it's providing listen before talk. Now, if we compare millions of transmissions with thousands and even with tens of thousands transmission realized by some other technologies, we can see the IQRF is capable to multiply battery life in real applications. That's the reason we have registered trademark IQRF True Low Power. On the other hand, as you would see from visualization, there is no magic behind, just the physics. For example, if we compare typical LP1 sensor sending its 12 bytes of data in 6 seconds at a consumption around 40 milliamps, logically the IQRF device sending 32 bytes of data in just 30 milliseconds and consuming 20 milliamps during transmission will drain battery for one packet 400 times less. It's very easy calculation. The next topic I will go through is interoperability. In the beginning, I should say the interoperability is very important. It simplifies design of IoT application and enables global cooperation of different vendors and integrators. How do IQRF assure interoperability? Let's take a look into hardware design. The heart of the transceiver module is the microcontroller. If we make abstraction of the microcontroller software layout, we will get 3 basic layers. 2 of them are responsible for interoperability. The IQRF operating system assures physical interoperability, and the IQRF DPA assures application interoperability. I believe the physical interoperability is clear, so let's take a closer look to the IQRF DPA protocol and commands. With the IQRF DPA, we can abstract the same IQRF transceiver module like a set of peripherals and services. Each peripheral or service is simply controlled by sending of the IQRF DPA command. Therefore, we named our interoperable transceivers as the IQRF data-controlled transceivers. As you can see on the top of the slide, the structure of the IQRF DPA command is standardized and consists from just few bytes. In the beginning of the data structure is network address, defining device address in the mesh network. Hardware PID is the unique identification for each specific device. Peripheral number identifies the peripheral or service we will use. For example, UART, LEDs, and so on. Peripheral command defines what should be processed in that peripheral. It can be, for example, open, close TX for UART, or switch on, switch off for LEDs. Finally, in the data block, there can be put some additional data or information. If you like, for example, actual temperature from device with the network address 10, we will simply create respective DPA request and send it to the network from the coordinator. As a response, we will receive temperature. We can even address FRC peripheral on coordinator and get actual temperatures from all sensors in the network in requested format, just by sending respective FRC requests. IQRF data control transceivers dramatically shorten development phase, and this results in a huge economical savings. Next topic is sometimes overlooked, but security is extremely important part of the whole design of any IoT device. I can even say the security is a must and should be considered also as an added value. On the following few examples you may see, the complex approach to the security should be taken, because omitting of any single detail can be consequently misused as a security flaw, and it's related to any technology. You have already seen this picture when I explained to you the IQRF positioning. Here, I use it for demonstrations that the security for wireless networks is even more important. Why? Imagine malicious user. With the wireless technologies, the access to the device can be realized remotely, without physical access. Finally, there is plenty of nice RF tools normally used, for example, for analyzing. On the other hand, the same tools can be misused for spying or forging packets. I can mention Hack RF1, Lime SDR, and even small SDR RF sticks one can get for just few bucks from China. All of them can be misused by malicious users. Let's see how the IQRF handles some security threats. The IQRF security is based on standards. Configuration and updates can be made via IQRF DPA over the air. The IQRF runs over 500,000 devices worldwide, and since 2004. The IQRF is not using golden keys. There are 128 bits network keys, 128 bits user keys, and the same size access passwords. The IQRF implements multi-layer security. Network packets are automatically encrypted. Security is complex, including also keys management and security isolations mechanisms. In 2021, the so-called one-time key bonding mechanism was added. It enables secure and simple mechanism for new devices to join the network. Information: the wireless is using shared medium and there are modern-looking RF tools. We consider it as the facts in the new protocol designs. Anyhow, as you may see, the IQRF found the answer to all identified and fixable threats. The next topic is documentation. On the IQRF.org and on the doc IQRF.org, you can find tons of materials, papers, application notes, guides, data sheets, facts, and even detailed technology descriptions and visualization. All these materials we created since 2004. So, where is the IQRF going to? In my presentation, I visualized just a few details of the IQRF mission to deliver low power, simple to adopt, secure, and interoperable wireless mesh connectivity for IoT. I'm really proud that our team hard work and all innovations we have created since 2004. Our next focus will be not anymore only technical. We are focusing now on standardization and opening all innovations we have created to the wide R&D community because we do believe in interoperability, community, and freedom. And because we do believe only with the wide and global community, the IQRF may become number one wireless mesh technology for IoT. In the end of my presentation, I would like to thank the IQRF team for the great job they did and still do, to the IQRF Alliance members for joining our passion and supporting the IQRF, and also to the Czech Ministry of Industry and Trade for financial support of the project FV40132. And of course, I should thank also you for your attention. Thank you very much.